Let me write down the official definition of a limit as x approaches some specific number. It's going to involve that epsilon Greek letter again and delta. It's going to be pretty hard to understand. We're going to try to understand it intuitively. So here's the official definition of a limit. As x approaches some specific number, call it c, of some function f of x equaling L. This definition in all its glory. Before I write it down, you need to realize that Newton, the great Isaac Newton, and his competitor Leibniz did not know this definition. Yet they are the creators of calculus. Huh? You can create something that you don't fully understand. Newton and Leibniz created calculus, but they didn't fully understand it. That's because calculus is very, very deep. It's taken, they created it in the 1600s, late 1600s. Here, 300 and some years later, you might say we still don't fully understand it. It's morphed into a new subject called analysis. Real analysis, complex analysis. That's a much more advanced subject, much deeper subject, even than calculus. And there's still new things to discover in analysis that people never discovered before. It's a very deep subject. The universe that God has created is very deep. It's infinitely complex. Infinity is really big. That's my blog if you want to look that up. This definition was not created, you might say, by humanity until 150 years after Newton and Leibniz. I think even a little longer, 170 years after they created calculus. It's created by, you might say, Cauchy. Don't say Cauchy, Cauchy. And, well, don't say Weierstrass, say Weierstrass. Cauchy and Weierstrass, Cauchy, French, Weierstrass, German. Mostly Weierstrass created this definition. Cauchy had a less precise version. This means, I should put the word means in here, means for all epsilon greater than 0, there exists a delta greater than 0 such that the following is true. The following implication: if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. Whoa. Looks like a foreign language, doesn't it? Well, yeah, there's Greek letters in there. But of course, there's plenty of English words too. How in the world do you understand what this is talking about? Here's something I've tested people on before to understand it at this level. Say you've got a function and you're graphing it on your calculator. Okay, so this one I'm drawing here is supposed to be a calculator window. Calculator window. And this is going to be like the x-axis here. And this is going to be like the y-axis here. Although that may not be the origin there. Not necessarily the origin. Not necessarily the origin right there. You think that the limit of this function as x approaches the number c, which is going to be right there, is the number L, which is going to be right there. C is an input, L's a possible output. You think that's true. How would you prove it's true? You need to prove that this definition is satisfied. Give me an epsilon, an arbitrarily small, we talked about this last week, distance from L in the vertical direction. really going between L minus epsilon to L plus epsilon. Give me an arbitrarily small number, could be 10 to the negative million power, that small. If what's this? What's the absolute value of this difference? That's the distance between those two numbers. You ever learn that the absolute value of a difference of two numbers is the distance between them on a number line? Give it a try. Absolute value of 5 minus negative 7 is the distance between 5 and negative 7 on a number line, 12. And it doesn't matter what order you write the numbers in. Absolute value of negative 7 minus 5 is also 12. And yes, on a number line, the distance between negative 7 and 5 is 12. That's just a shorthand way of saying the distance between x and c is less than delta. And not equal to 0 because maybe the function is not defined at c. Maybe it's got a removable discontinuity there. We want to allow for that possibility. And in fact, we even want to emphasize the function doesn't have to be defined at 0. So we're saying here is if the absolute value of x minus c is less than delta, if x is within delta units of c, not necessarily equal to c, between c minus delta and c plus delta, that the distance between the function outputs and L is less than epsilon, which means the graph is in this picture and exits the screen through the left and right-hand sides, not through the top or the bottom. If it exits the screen, the computer screen, the calculator screen on the left and right-hand sides, that's enough, and stays in the screen for all x in here, that's enough to say that the distance between f of x and L is always less than epsilon. Now, again, maybe it's got a removable discontinuity there. Maybe just I'll go ahead and draw a removable discontinuity just for the sake of doing so. But it may not be a discontinuity. It may be continuous there. It's the fact that we can do this no matter how small epsilon is. We can find a delta that works that makes this, this definition work. Let's do an example. Going back to our old standby here that we've been doing the past few days. 3x minus 7. We're letting x approach 4. You remember what the limit was? 3 times 4 minus 7 is 5. Picking your window here is essential. First, I'm trying to pick it in the y direction, actually, near 5. How close to 5? Well, let's go 4.9 to 5.1. 0.01 for the scale, just to make tick marks. I want x to be going to 4. Close to 4. How about 3.9 to 4.1? Let's just see what we see when we graph this. We do see the graph, but it's not exiting through the sides. What does that mean? It means there are values of x over here in the left and right where the function outputs are too high or too low. They're more than 0.1 units away from 5. So does that mean the limit's not 5? No, it just means you didn't pick your delta small enough. Remember that proof from last Friday? I picked delta to be epsilon over 3. So instead of 3.9 to 4.1, I should probably try 3.96667 to 4.0 33333. Why? Because 0.1 divided by 3 is 0.0333333 repeating. Now, if I graph this, probably the graph's going to go right through the corners. Yep. And if I make my window even smaller in the x direction, say 3.98 to 4.02, so my delta is 0.02, then it definitely exits through the sides. Now for all x down here, the y coordinates are in here. They are within epsilon of 5. And I can do that no matter what epsilon is. I could go back to my window and pick something closer to 5 here, like 4.99 to 5.01. If I don't adjust my delta, I'm back to the first situation and it's exiting through the top and the bottom. But I can always readjust my delta. Go even smaller, 3.998 to 4.002. Now it's working. And no matter how small delta epsilon is, I can find a smaller delta that'll work. This is the kind of thing that I have tested people on with this concept, is understanding the relationship between this definition and what we're seeing on the calculator. And it comes up on homework too. Maybe it even already did. And why does this mean the limit is L? You know, couldn't it be possible that the true limit is not exactly 5, but maybe 5.001? Calculator, could the limit possibly be 5.001? Why don't I center it at 5.001? Well, or to keep it simpler, how about 5.1 just to keep it simpler? What if I go from 5.09 to 5.11? What am I going to see now? I don't see anything. Do I need to pick delta to be smaller? 3.999999 to 4.00001? That work? No, I still don't see anything. I would see something if I picked a bigger window. 3 to 5, say, I would see something. There it is. It looks very steep. In the y direction, this is not centered at 5. It's centered at 5.1, which is not the limit. The problem here is if I make smaller and smaller deltas, I eventually get to a point where the graph's not even in the picture. I think it's gonna keep moving to the right here, I think. Yeah, I'm eventually getting to a point as x gets closer and closer to 4, where effectively we don't see the graph at all because it's off the screen to the right. That's what happened. That's why the limit's not 5.1. And you can do something similar if you thought the limit might be 5.01. To tell you the truth, these definitions are most important for proving facts that seem fairly obvious, and you have already used, in fact. I did talk about these last Wednesday. Properties of limits, for example, like these. Take this property, for example, property 2. What is that saying? It's saying the limit of a sum of two functions is equal to the sum of the individual limits. Intuitively, for example, pretend f of x is getting close to 5 and g of x is getting close to 7 as x approaches c. What is f of x plus g of x getting close to? Well, if the outputs of f are getting close to 5 and the outputs of g are getting close to 7, it should make sense that the answer is getting close to 5 plus 7, 12. Intuitively, this seems reasonable. And it works for multiplication and division as well, as long as you're not dividing by 0. But to prove these rigorously, and to allow for weird examples that might oscillate infinitely often, for example, to be really sure you're not just dealing with trivial examples here, you want to prove these using a precise definition. And that Epsilon-Delta definition is just what the doctor ordered to prove these things. Now, we're not going to do those proofs because they're too hard. I'm trying to get across what's really the basic idea, even though it seems hard. I'm not saying it's easy when I say that. It is hard. Newton and Leibniz didn't know it. They were geniuses. It took 150 years to get to the point where people figured out that's the right definition. And then they were able to prove things. That's the harder part. Okay. You can use these properties anytime you need them. They're really convenient. To finish this, let me just reiterate what I said. For all epsilon greater than 0, no matter how small, 0.1, 0.01, 10 to the negative 10, 10 to the negative 100, 10 to the negative million, it doesn't matter. Microscopically tiny, smaller than the smallest atom. I'm serious. This is how small epsilon could be. No matter how close you are to L in this direction, there's a closeness delta in the x direction to c, so that the distance between x and c is between 0 and delta, meaning X is in this window somewhere, but not equal to C because maybe there's a removable discontinuity there. Maybe your function is not defined there. If you can find such a delta that when this is true, then this is true, meaning for all the inputs in here except possibly at C, the outputs are within epsilon of L. That's what it means for the limit to truly be L. And it's the arbitrariness of the epsilon. It can be arbitrarily small that really makes this work.